Good morning, all. I'm Praveen Bolini. Thank you for attending my talk at the AICHE meeting, virtually, of course. Today, I'm going to be talking about characterizing the density and speciation of open metal sites in metal organic frameworks, and I'm going to be doing this specifically for the case of MIL 100 chromium. I'll go through this process in four specific steps. First, I'm going to describe why we chose MIL 100 chromium as the material of choice and what our motivation is for developing a method for characterizing open metal density and speciation. Secondly, I'll go into the protocols and concepts that we used to quantify open metal sites. Then I'll go in and discuss how we monitored open metal site creation and verified the validity of these techniques. And lastly, I'll show you how these techniques open up the opportunity to probe not just the density, but also the speciation and specifically the oxidation state of open metal sites. So let me first go into what MIL 100 chromium is and why we need a method to characterize open metal density. So the node in MIL 100 chromium is comprised of a trimeric oxo node. So I have this oxygen atom, which is connected to three metal atoms that in this case is chromium. These metal atoms are interconnected through trimesate linkers, and these nodes, which are connected through trimesate linkers, form an extended secondary structure comprised of two mesoporous cages, one 6 angstroms in window diameter and the other 9 angstroms in window diameter. Now, if I look at the node more closely, I have per node two water molecules that act as labile ligands, and I have a third ligand, which is an anion that is typically either fluorine or a hydroxyl, and in some cases a nitrate. This anion is essential from the standpoint of balancing the charge on this trimeric oxo node. Now I can activate this material at higher temperatures, and typically at temperatures below 150 C, I can eliminate the water molecules to form metals in the +3 oxidation state, and above 150 degrees Celsius, I can eliminate the anion and concurrently reduce my open metal site to a +2 oxidation state. So one of the main reasons we're interested in these kinds of oxo-centered nodes is the availability or the opportunity to create reduced open metal sites in specific coordination environments for the oxidation of light alkanes. For the purposes of this talk, I'm going to exclusively be focusing on the open metal site creation and the question of redox catalysis properties or redox conversion properties of light alkanes over these kinds of materials is going to be taken up by my student Jacqueline Hall at an oral presentation on Thursday. So what are the current methods that are typically used to quantify open metal sites? There are three that I can think of. The first is using CO adsorption. The main disadvantage of using CO adsorption, the limitation here, is the fact that you can have incomplete saturation at ambient conditions, and typically you would require going to subambient temperatures to achieve complete coverage of the open metal sites. There is also the question of unselective CO adsorption and dealing with and deconvoluting unselective from selective adsorption. The question of selective adsorption becomes even more important and even more of a hindrance if I look at pyridine adsorption onto open metal sites. Pyridine, of course, can adsorb not just onto open metal Lewis acid sites, but also onto bronze acid sites that originate from the labile water ligands. Lastly, ammonia TPD protocols that are typically used to characterize acid site densities in materials like zeolites may not be applicable widely to MOF materials due to the limited thermal stability of MOF materials as a general rule. So clearly, there's a need to develop methods that can help us quantify open metal site density, and we have MIL 100 chromium as a prototypical MOF that would allow us to do this. So next, let me go into the method that we use to quantify open metal site density. The method that we use to quantify open metal site density has at its heart the use of water adsorption isotherms. Specifically, we hypothesized that water adsorbed onto open metal sites would adsorb irreversibly at room temperature, whereas water adsorbed elsewhere onto the MOF at room temperature would be adsorbed reversibly. So here's the protocol we went through in order to test this hypothesis. So we look at the as synthesized MOF here with water molecules adsorbed onto the chromium sites and elsewhere in the material. If this material is evacuated at a high enough temperature, in this case 250 degrees Celsius, I can get rid of all of the water molecules adsorbed onto the open metal sites. I can then bring in water at room temperature and measure an adsorption isotherm. What does this isotherm look like? It has many different stages in the adsorption that it exhibits. So if I look specifically after the region where the open metal sites are covered with water, I see two separate sharp uptakes. The first, which is at relatively lower pressures, is adsorption into the 25 angstrom cages, and the second stage is adsorption into the is capillary condensation into the 29 angstrom cavities. Next, what I can do is I can evacuate this material at room temperature, and if my hypothesis is correct, I would get rid of all of the adsorbed water except for the water adsorbed onto the open metal chromium. And I can measure a second adsorption isotherm, which I will refer to as a difference isotherm. So here's what the difference isotherm looks like relative to the originally measured adsorption isotherm. As expected, the difference isotherm lies below the isotherm for the material that was originally activated at 250 degrees Celsius. Moreover, if we look at the region that is past the adsorption into the larger mesoporous cavity, we see that the difference between the original isotherm and the difference isotherm approximates to the density of open metal chromium, or the density of chromium in my metal organic framework material. I won't go into the reasons why you specifically have to look at the region past the second capillary condensation step, but I'm happy to discuss that further if you have any questions that you would like to point at me. So obviously, we're looking at the material that has all of the open metal chromium, potential open metal chromium available as open metal sites. What we expect is that by varying systematically the activation temperature, we can go from no open metal sites at lower temperatures to activating all of the open metal sites at higher temperatures. And consistent with this expectation, when we use the difference between the original isotherm and the difference isotherm, we do observe the expected trend, which is that the fraction of open metal chromium increases monotonically with activation temperature and reaches a value of 1 at temperature of 250 degrees Celsius, where I access all of my possible open metal chromium. So I've shown you that we get systematic trends that are consistent with our expectations and hypotheses when using the presented method of water adsorption for open metal site quantification. Now let's go in and see if we can monitor open metal site creation and thereby verify the site counts, open metal site counts that we obtain from water adsorption. To do this, we use infrared spectroscopy, and a key choice that was made in the process of these studies in being able to use infrared spectroscopy for these verifications is the choice of anion. So we intentionally synthesize a material that has a hydroxyl anion that is the exclusive anion on this metal organic framework material, rather than using a fluoride anion, which would not allow us to accurately quantify the anion removal using infrared spectroscopy techniques. The advantage of using a hydroxyl variant of MIL100 becomes immediately clear once we look at the infrared spectroscopy data in the region that corresponds to the hydroxyl vibrations. So I see two separate peaks here, the one at higher wave numbers corresponding to water coordinated to chromium, and the one at lower wave numbers which corresponds to hydroxyls coordinated to chromium. When I increase the temperature, I observe a systematic decrease in both these peak areas with increasing temperature. Is I can use the fractional reduction of each of these peaks as a function of activation temperature to obtain the open metal site fraction. Now I can take these open metal site fractions with what I obtain from water adsorption from the difference between the original and difference isotherm, and what I observe is a one-to-one correlation between the estimated fraction using infrared spectroscopy and irreversible water adsorption, thereby at least partly validating the methods that we're using to quantify open metal site densities. So what I've shown you is not only that we can get meaningful trends and test out our hypotheses, but also that we can compare infrared spectroscopy data and irreversible water adsorption data to verify the site counts that we obtain using these two methods. Now, what this allows us to do and what it opens up the possibility for is to systematically probe not just the total number of open metal sites that we have, but also the number of sites that are in a specific oxidation state on this MIL-100 node. Next, and so as I've shown you previously, we observe a decrease in both the number of water molecules coordinated to chromium as well as the hydroxyl anions. The removal of these hydroxyl anions simply due to charge balancing constraints should correspond to the creation of reduced open metal sites. But so far, we've not provided you any evidence for Cr2 plus formation. It can be overcome if we bring in NO and bind it to Cr2 plus. These experiments are done at room temperature, but they're done as a function of activation temperature. And when we bring in NO, what we see is that NO binds selectively to Cr2 plus sites at room temperature, but not Cr3 plus sites, as noted from the lack of the NO, the lack of the nitrosyl corresponding to binding to Cr3 plus. We can go and we can estimate the fraction of hydroxyl removal. We can also take the peak of the peak obtained upon exposure of the MIL-100 to NO and calculate a Cr2 fraction from the NO adsorption data. What we observe again is a one-to-one correlation between the Cr2 plus fraction obtained from these two methods, thereby validating this reduced open metal site densities estimated these techniques. Not only NO, but so what we see here is that in addition to the site fraction of total chromium, I can also partition these and provide you with the fraction of sites that are Cr2 pluses and Cr3 pluses at any activation temperature. And a key observation here is that at a temperature of 150 degrees C, I start to observe a significant density of Cr2 plus sites, unlike lower temperatures where I do not observe a significant density of Cr2 plus sites, only Cr3 plus sites. So we use CO as a molecule that binds selectively to Cr2 plus sites as a result of pi backbonding interactions that occur with the Cr2 plus sites over Cr3 plus sites. If I bring in carbon monoxide and measure the adsorption isotherms as a function of activation temperature, I see a systematic increase with increasing activation temperature. Not only that, but also I see that my CO adsorbed at 0.1 bar tracks systematically with the Cr2 plus fraction that I estimate either from infrared spectroscopy or in the presence or absence of NO. I can take this one step further. I can bring in ethylene, which also again has a pi bond that can have backbonding interactions with Cr2 plus sites. I see a significant increase in uptake at or about 1 degree Celsius, unlike the ethane adsorption data, which shows a more systematic trend as a function of activation temperature. Again, presumably because of enhanced by back bonding interactions of ethylene with Cr2 plus sites. The trends become even clearer if I plot selectivities as a function of activation temperature. Clearly, the materials activated below 150 degrees C are almost unselective to ethylene, whereas those that are activated at or above 150 degrees Celsius are significantly more selective to ethylene, with increasing activation temperatures leading to a higher ethylene selectivity owing to the higher Cr2 plus site fraction. So what I've shown you here is I've shown you a method that may be universally applicable to quantifying open metal site densities in MOF materials, verified the validity of the method, at least for this class of materials. And also, I've shown you how this allows us to probe site speciation and the density of reduced open metal sites in MIL 100 type materials. I want to take a quick moment to acknowledge my group, and specifically Jacqueline Hall, who did all of the work that was described in this presentation, and ACSPRF and various UH internal funding sources for funding this research. And a quick note that the entire story and the work that was focused on open metal site creation, quantification, and characterization was it was essentially a necessary step in being able to evaluate not just the separation properties of these materials, which are very promising, but also the low temperature alkane oxidation properties of this material. That's something that will be taken up by my student Jacqueline Hall, and I would strongly encourage you to attend her talk on Thursday morning, which is in the microporous and mesoporous materials metal chemistry session of AICHE, if that's something that interests you. With that, I'd like to conclude my presentation. I thank you for your attention, and I'd be happy to answer any questions virtually.